Nuclear energy is a huge part of our society, and nuclear energy has been touted at times in the past and the present as being a real cool method to get a lot of energy. And we're a hungry society for energy, all right? We need the energy for cars, we need the energy for making aluminum things and making cell phones, computers, stuff like that. Even AI needs a lot of energy to make it happen. So, one thing that people think about a lot is what's called transmutation, which is converting one nucleus into the other. And this will only happen if you have a process called fusion or fission. So first, we're going to talk about nuclear fusion. And nuclear fusion involves two smaller nuclei. So hydrogen, helium, lithium, maybe something like that. And they will essentially smash into each other, but so powerful that they actually create new atoms, which is just amazing. And sometimes a neutron will get kicked out or something like that. But the energy output is just phenomenal. All right. So in the reaction shown there at the bottom with deuterium, hydrogen 2, and tritium, hydrogen 3, you make essentially an alpha particle, helium 4, and a neutron. But the energy that comes out, minus 1.7 times 10 to the ninth kilojoules per mole. It's just fantastic. The nice thing about nuclear fusion is that the products are very clean. You have a lot of energy. There's no meltdown, as we'll talk about with fission here in a little bit. However, to make fusion happen, you have to have plasma. Plasma is a fourth state of matter we'll talk about. You need really high temperatures. It's very hard to sustain plasma and to sustain nuclear fusion, although it's coming. All right, I really believe it's coming. So in the lower right-hand corner is an example of what's called a tokamak reactor. That's a place where if you imagine the plasma kind of circles around, and that allows then the nuclei to smash into each other to create the nuclear fusion. But it's not an easy process, although the technology is getting there, and I sure hope that one day we all have nuclear fusion as our primary energy source. Plasma is another state of matter, and we've spent a lot of time this quarter talking about gases and then solids and liquids, as you know. Those are the phases of matter which are most common on the Earth. But plasma, when you think about the whole universe, is actually more common than anything, so we should talk about it. Plasma is described as an electrically conducting fluid, all right? And the fluid will flow like all other things. However, the ions are just kind of roaming around. The electrons are different, separated from the protons and the nuclei. You need a really strong magnet to keep it together, electric fields, and it's very, very hot, all right, just incredibly hot. Now, it's rare on the Earth, but in the universe, it's really common. So sometimes people call the islands like Earth to be a lot different than the rest of the universe. The sun is basically a big plasma source, and the sun is much more massive than all the other planets combined, so that's why plasmas are definitely the number one type of matter, if you will, in the universe. Remember that in space, right, diamonds are actually pretty common and wood is rare. And in space, plasma is very common, but solids, liquids, and gases are relatively rare. So it just kind of shows the perspective of the Earth versus the rest of space, which is kind of a cool thing to think about in the back of your mind. This graph shows different sources of plasma, and again, in the upper right-hand corner, you've got the fusion of the sun, solar cores, all that kind of stuff, lots and lots and lots of plasma. However, if you've ever seen an eclipse, the corona around an eclipse, that's plasma, all right? It's plasma around the sun, but we can see it, which is really cool. Fluorescent lights use a form of plasma. Lightning involves plasma being created, which is really cool. So there is plasma around us all the time.
There's a match head. Yes. Nice.
This video was created by two of my students in 2010, and they're wonderful people, and I respect them so much. And they're in medical school; they're doing great things. But anyway, at the time, I said, "Oh well, plasma is really difficult to create and stuff like that. You need high energy and stuff like that." And they said, "Hey, what about the grape experiment in their microwave?" And I'm like, "What?" So anyway, these guys put a grape in their microwave with a match head, you can see, and when they turned the microwave on, this really bright light occurred, and I thought, no way, this isn't plasma, which is what they claimed it is. Well, I did some research, and I'm not convinced that it's not plasma. Okay, I'm not going to say I totally believe it's plasma. I still think it's some kind of reaction, maybe with the match head, but I can't totally kick out based on the research I did that it isn't plasma. So maybe you just saw plasma created in a microwave, and you can try this experiment too. I take no responsibility for any damage to your microwave because, again, plasma is a super high energy source, and I keep nervous. But they did it several times and made this video for me. So my hat's off to them. This has given me a lot of things to think about. It very well might be plasma. I can't totally say it's plasma, but I certainly can't say it's not plasma, which is where I started this whole research part. So again, my hat's off to them. And if you see a way to make plasma, you let me know as well.
Tokamak reactor is used to basically create the magnetic fields and control the heat that's necessary for making plasma. It's kind of like a donut, all right? And in the donut, then you have the different ions running around and around and around and around, and that's what allows the plasma to start happening. And again, this is not something you can do in your garage, at least not yet anyway. You need some pretty strong kind of protective currents in order to protect you and everything else around it. This is a video I was able to obtain from February of 2022. In the United Kingdom, they're creating this kind of thing, and it shows the actual tokamak reactor with the plasma running around, which is just amazing. But anyway, they were able to create more energy than they put in, 59 megajoules. So that would be 59 times 10 to the 6 joules, which is really, really cool. So come on, go, go, go. Anyway, so one day, hopefully this will be more possible, but we'll see what happens, of course. This picture shows the inside and outside views of the tokamak reactor. I think this was from Germany, but I'm not totally sure. Anyway, there's a person standing inside the tokamak reactor for scale comparison. And again, when the actual plasma is running around, this person would not be there, of course, but it's kind of cool. But outside, my goodness, this is an engineering marvel that it's able to even be constructed, because you have all these different kinds of electricity and cooling and heating and blah, blah, blah. It's amazing. But anyway, one day, I'm hoping this will be our primary energy source. So, for example, hydroelectric is what Oregon uses a lot, but hydroelectric has been controversial. It causes lands to be flooded and fishing areas to be messed up, stuff like that. Of course, I love solar power, the energies and stuff like wind power, but people sometimes don't like those. Oil and gas, of course, have been traditional powers that people have used. But fusion, man, if you could just make it, it would be so clean. I think it would be super cool, but, you know, what can you do?
In the nuclear fission of uranium-235, a neutron collides with a uranium atom, causing it to fission into two smaller nuclei. On the average, 3 neutrons are emitted for every U-235 atom that divides.
When people hear nuclear power, they usually are thinking of nuclear fission, and fission is different than fusion, okay? While fusion involved lighter nuclei becoming heavier, fission involves bigger nuclei becoming smaller. And usually what happens is you have a big element like that uranium-235, big here meaning lots of protons and lots of neutrons, and they essentially fire a neutron into it. It breaks up the bigger atom, and in this case it creates a krypton-91, a barium-142, and 3 neutrons, and you create lots of energy in the process, which is really cool. Now, about 17% of the world's energy is from fission. France is the leader. They have an incredible amount of nuclear fission reactors. I consider what France has done to be pretty cool. They're using some of the waste and recycling it, but you do need a neutron trigger, and you must keep these under control, as we'll see.
If the mass of U-235 is less than the critical mass, no chain reaction will result. Most of the neutrons will escape to the surroundings. If the mass is critical, most of the neutrons will be captured by other U-235 atoms, and an uncontrollable chain reaction will occur. This is the explosion of a thermonuclear bomb.
Now, nuclear fission does create a lot of energy, and the technology is more or less available to us right now for using nuclear fission. But there are some problems, all right? So, first of all, let's talk about the waste. When you have nuclear fission, you make smaller nuclei, but it's not like helium and stuff like that that's easy to control. You're going to have some really bad kind of radioactive wastes around. So, when it comes to nuclear fission, you have to think about what you're going to do with the waste. And what people have usually done is they've buried it in a big hole or something like that and just said, do not come back for 2,000 years or whatever. And the half-lives are crazy, but that's another thing. So the waste particles must be considered. France has done a great job in recycling a lot of the waste, which really impresses me, by the way, which is pretty cool. Another thing that's really important to realize is that nuclear fission can result in nuclear explosions, all right? Fusion can too, but the energy for keeping the plasma up just dies out, so you won't really have that problem. But with fission, this is definitely something to consider. And there have been some problems, as we'll see later, with fission reactors. However, that being said, there's more than 400 nuclear fission plants in 30 different countries. The United States has about 100 of them working right now. Now, in the middle lower part, I feel it's important to talk about the Trojan nuclear power plant. This was actually a fission processed nuclear fission power plant in Oregon. It was kind of by Rainier, Oregon, in northwestern Oregon. And this picture was taken in 1973. And I visited this place. That orange building was kind of like a little OMSI. You could go in there and see all these cool displays about nuclear power, blah, blah, blah. However, it was also some problems, all right? The things that created the electricity were breaking down. There were some problems of containment, et cetera, et cetera. So one day they finally just shut down. They imploded the cooling tower, that kind of tall thing right there. And so now you wouldn't know it was even there. I think there's a park with maybe a plaque or something, but it certainly isn't what it used to be. So Oregon did try nuclear fission, but it just didn't work out for Oregon. All right. And that's what some other countries have seen too. We'll talk more about the safety of things. Anyway, in this process, though, the energy that's created basically heats water, and the water goes through several things to basically move a generator to create electricity. And that's where electricity comes from. And they would do something like this with fusion too, which is kind of cool. Pretty exciting.
Located in the nuclear core of a fission reactor are fuel rods, moderator and coolant fluid, and control rods. Each fuel rod contains tiny pellets of uranium dioxide. In these hundreds of fuel rods, fission occurs, producing an average of 2.5 neutrons per fission reaction. The fuel rods are surrounded by water, which acts as a moderator by colliding with the neutrons and slowing them to a low thermal level. The water absorbs the thermal energy, which is used to drive a steam turbine to generate electricity. The low-energy neutrons enter other fuel rods and collide with uranium-235 nuclei, creating additional fission chain reactions and the release of more neutrons. The amount of low-energy neutrons present is regulated by control rods made of boron, which are very effective at absorbing neutrons. These rods are raised out of or lowered into the core as needed to sustain the chain reaction at the desired level.
On social media, I follow several nuclear energy kind of groups and stuff, and I'm always fascinated by what they say. And truth be told, there's a lot of power when it comes to nuclear fission, all right? Because, wow, you get a lot of energy out. It can create electricity. You don't have to rely on Middle Eastern oil, which is sometimes a little politically charged and stuff like that. But again, you do have the waste, which is bad. One day, I think fusion will make the fission process not as attractive, but anyway, that's still, the technology isn't there yet. It's getting there, but it's not quite there yet. However, with nuclear fission, there's also been what are called problem events, and I want to talk about those real fast. The first problem event was actually from 1961 in Idaho Falls, Idaho, our neighbor next door. And several people, I think 3 people actually died as the result of a nuclear reactor problem they had. And they kind of hushed this up. I just found out about this not too long ago. If history is your thing, you might find that interesting. However, in 1979 was 3 Mile Island, which was a series of nuclear fission plants in Pennsylvania. And they definitely evacuated a lot of people. They thought it was going to blow, but they were able to control it and stuff in time, no problem. But it was very scary. People talked about that for a long time. What was really scary was in 1986 in the Chernobyl reactor in the Ukraine. And oh man, that one had some serious problems. There was an HBO series about this, which was just terrifying to me. Other countries weren't told about this until several days after, so it was a political nightmare as well as the nuclear radiation. That's a fascinating subject too. So Chernobyl is still heavily radiated. It's a very dangerous area. You want to be very careful. Pretty crazy. In 2011, Fukushima in Japan was another place where they had a nuclear incident. All right. There was an earthquake caused a tsunami, and the tsunami came in and wiped out lots of their nuclear power plants, and it created a lot of contamination of the whole area. Very sad, although actually the radiation from that has been less than I thought it was going to be, which is pretty cool. But again, another thing worth checking out. But what I really want to highlight here is Hanford, Washington, and we live here in Gresham right along the Columbia River. If you go upriver, kind of over by the Tri-Cities, that's where this Hanford nuclear power plant is. And part of World War II, they were developing some of the tools for their nuclear bombs in Hanford. And since then, they did lots of nuclear work. The problem with Hanford, though, is that they just put all their waste in basically a hole. And the hole is next to the Columbia, and the Columbia, the groundwater can get into the Columbia, and that water comes right down us here by Portland, Oregon, and Gresham, Oregon. So Hanford is a nuclear mess, all right? They've done some really cool science, and I love touring it. It was fascinating. It was a really, really cool thing to see how the uranium was turned into plutonium and stuff like that. However, it's definitely something that we should be concerned about as residents who live downstream of Hanford. So anyway, I'm off my soapbox, but just be a little careful when people say that fission is so cool, because maybe one day it will be, but right now there have been some problems with fission, and it makes me nervous when I do it. But fusion, on the other hand, green light, sounds cool. See what the future holds.